All right, next. Yeah, again, that's the highest n. So n is equal to 4, it's higher. That's a bigger orbital. You know, n equals 3, n equals 4, n equals 5. Let's go bigger. So that's a bit of a tricky question. Number 10, stoichiometry, methane combustion, CH4, O2, CO2, water. How many pounds of methane burn for every 1.0 pounds of CO2 formed? So this is straight stoichiometry. So we're going to go from pounds of CO2 to grams of CO2, grams of CO2 to moles of CO2, moles of CO2 to moles of methane, moles of methane to grams of methane, grams of methane to pounds of methane. Methane weighs less than CO2, so it's going to be less than a pound. 0.54, 0.74, 0.36. 11 is another stoichiometry problem. Nitrogen plus 3 hydrogens yields 2 ammonia. What mass of hydrogen is required to make 25 grams of ammonia if the percent yield for this reaction is expected to be 88.8%? So we have to prepare extra in anticipation of losing about 11.2% of it. And so we have to do one of these. Similar to the cookie that we did earlier. Is C6H12O6 is glucose, sugar, or carbohydrate. The carbohydrate oxidation or combustion there. This is delta H of minus 2.82 times 10 to the third kilojoules. What mass of glucose is required to produce 1,000 calories with a capital C? Calories with a capital C are food calories. So 1 food calorie is equal to 1,000 chemical calories. So 1,000 calories, we're going to go from calories to food calories to chemical calories to joules, joules to kilojoules, kilojoules to moles. So we get this many kilojoules per 1 mole of glucose reacting there. 13, this would be like photosynthesis. CO2 plus water yields glucose plus O2. Calculate the percent yield at 5.2 grams of CO2 yields 2.8 grams of glucose. And so in theory, how much glucose should you get from 5.2 grams of CO2? We could calculate it. Go from grams of CO2 to moles of CO2, moles of CO2 to moles of glucose to grams. That's how much we should get. But this is the actual yield, which is 2.8 grams. So it looks like it's going to be less than 100%. 14, n equals infinity is allowed. Yes. 15, BF3 contains a double bond to get an octagon boron. Well, we could draw out the Lewis structure for BF3, unless you remember seeing BF3. How many electrons do I have? Is that the Lewis structure for BF3? What's wrong with my Lewis structure? Well, the question's asking if there's a double bond, but I don't need a double bond. I can do it with single bonds. Take a look at my structure. Too many electrons. How many electrons am I allowed? I have 26 electrons. I have way too many electrons. Yes. Sometimes we don't have to total it up. I could see that this is the right number of electrons because boron has 3 valence electrons. These 3 valence electrons here. Fluorine has 7 valence electrons. So I have fluorine giving 7, boron giving 3, so it all adds up. So I don't have to sum total. I already see that this is the correct number of electrons. But one thing boron doesn't have is what? An octet. Well, that's easy. Just erase this pair and make a double bond. Why not? Oh yeah, fluorine. Okay, there's a rule. There's a rule. Fluorine only forms single bonds. It's a pretty good rule. Fluorine only forms single bonds, and so it shouldn't form a double bond. Why? Why does fluorine only form single bonds? Yeah, that's why. It's very electronegative. And so if we look at the formal charges here, the formal charge on fluorine is plus and the formal charge on boron is minus. So this formal charge arrangement is unrealistic. It's unrealistic for fluorine to give up an electron to boron. Boron's electronegativity is 2, fluorine's a 4, so it's not going to happen. Here. And so the answer is this goes with less than an octet. And so there's no double bond. So the answer to this is false. It does not contain a double bond. Heisenberg determined that the electron's position must be given by an electron probability cloud. True. 17. Modern day scientists visualize electrons occupying orbits around the nucleus. Yeah, orbitals. That's false. 18. 2D orbitals are forbidden. That's true. 19. Orbitals describe the energy and positional probability of electrons in atoms.
True.
That's true. This is a bad question, I realize. But we can do what we would expect, because I told you don't have to memorize the little blips in there. Oxygen has a higher ionization energy than nitrogen because it has more protons. Should be true. It's true. Helium. Is helium bigger or smaller than hydrogen? It's smaller. Why? It has more protons. What's easier to ionize, a bigger atom or a smaller atom? Bigger atom's easier to ionize. Smaller atom's harder to ionize. Helium's going to be harder to ionize, meaning it has a higher ionization energy. And so oxygen's smaller than nitrogen, so oxygen should be harder to ionize. Why is it smaller? Because it has more proton. In the same shell, you know, oxygen and nitrogen on the same shell. But there's a little blip there because it's a paired electron we're ionizing versus an unpaired electron, so should have picked another one. 21. The fourth shell of a multi-electron atom contains how many sublevels or subshells? The fourth shell contains how many subshells? 3. Right. Actually, we can just see it from the periodic table. 1, 2, 3, fourth shell. This is the 4s, the 3d, and the 4p. It's 3. 3 subshells, the S, the D, and the P. number was that? 21. 22. "3D orbitals violate quantum mechanics because of L." Well, do 3D orbitals violate quantum mechanics? No. 3D orbitals are allowed. 23. The electron configuration for nickel excuse me, is argon 4s2 3d8. Is that true or false?
True.
It's true. Electron configuration for nickel is argon 4s2 3d8. The electron configuration for nickel 2 plus is argon 4s2 3d6.
True. False.
False. Why is it false?
Because of them make it iron.
It could be isoelectronic with iron. It doesn't make it iron. It just makes it have the same number of electrons as iron. That's okay. It's false for another reason. Well, what's the correct electron configuration? It does lose 2 electrons. That's correct. Well, nickel 2 plus loses 2 electrons. Which electrons would be easiest to lose? The 4s or the 3d? The 4s, because the 4s are further away from the nucleus, because the 4s are called the valence electrons. The valence electrons are the electrons that are furthest away from the nucleus, which would be the 4. And so a nickel 2 plus has the electron configuration argon 3d8. That's correct. Because we're going to strip the 4s, the valence electrons come off first. If they're the furthest away, then the obvious question is, why do they fill before the 3d? Because when we fill it, we fill the 4s and then the 3d. And so it's a bit tricky. It's because of how we look at distances, probability, and that kind of stuff. It's because of the shape of the cloud. Shape of the cloud you talk about in Chem 1A, not Chem 4. So we aren't going to get into it. Just we're going to ionize the highest end. That's why sometimes it's written in the order you fill it. Sometimes it's written in the order that they're removed. Okay, 25. The electron configuration for fluoride ion is helium 2s2 2p6. Is that true or false?
False.
False? What is it?
2s2 2p5.
2s2 2p5 is for fluorine.
Oh, right.
Fluoride would be 2s2 2p. Well, anyway, fluorine is, you're right, helium or 2s2 or 1s2 or helium, 2s1, 2s2, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5. That's fluorine. Fluoride has an extra electron, so it would be going from 2p5 to 2p6. And so it's true. It's helium 2s2 2p6, or another way of writing that would be neon. So helium 2s2 2p6 is equal to neon. When we say neon, it doesn't mean fluorine converts into neon. It means fluorine gets the same number of electrons as neon. In other words, fluoride doesn't want to lose those electrons. Fluoride is the worst reducing agent on the periodic table, meaning that it does not lose those electrons, meaning that it's kind of unreactive. It's stable like neon in certain ways. Fluoride is not a very dangerous redox reagent. But a lot of people are scared of fluoride because fluoride is a dangerous metathesis reagent. Fluoride is a very dangerous metathesis reagent because precipitation of calcium fluoride is very favorable. So let's say if there's too much fluoride in your toothpaste, your teeth are going to be in trouble because you're going to precipitate too much calcium fluoride out of your teeth, which creates mottled teeth. But, you know, as far as redox, it's pretty. This is what happens if you have too much fluoride. Your bones suffer, your teeth suffer. Too much fluoride. Just the right amount of fluoride is great. If you have just the right amount, you're going to have beautiful teeth. Too little fluoride, your teeth suffer. Too much fluoride, your teeth suffer. You just need the right amount. That's stoichiometry. That's why we need stoichiometry. Figure out how much. It's just the right amount. But fluoride as a reducing agent is the worst. Fluoride is the worst reducing agent on the chart. It means it's pretty stable. Okay, let's go on to next. Bromine has 7 valence electrons. 4s2, 4p5. Is that correct? Xenon, 4s2, 4p5. Well, bromine, is it true that it has 7 valence electrons?
Yes.
Yes, that's true.
It should be argon.
It should be what?
Argon, not xenon.
Yeah. Right. Not only that, there's one more error. What's the additional error?
It's missing the D orbital.
Yeah, we're missing the D's. So it should be this. It should be argon, 4s2, 3d10, 4p5. How many valence electrons is that? So bromine has 7 valence electrons. And this electron configuration is argon, 4s2, 3d10, 4p5. Some people will tell me it has 17 valence electrons. In fact, I need to add 10 more dots around here. 17 valence electrons. Does that look right? No. It has 7. It's the highest 10. Highest 10. Which bond is least polar? HN, correct. Nitrogen's the least electronegative. Fluorine's the most, then oxygen, then nitrogen. Let's just based on, oxygen's closer to fluorine than nitrogen. Whatever's closest to fluorine. 28, the charge on the halide ion is, halides would be like the chlorine, bromine, iodine. Or the halogens, the halides would be chloride, bromide, iodide. Which all have charges of -1. 29, core electrons do not participate in chemical reactions. That's pretty much true, except for the transition metals. Transition metals, you might have the Ds participate, the 3D. 30. Bonds in hydrocarbons are best categorized as nonpolar covalent, yeah. Carbon is a 2.6. Hydrogen is a 2.2. So the difference is 0.4. The carbon-hydrogen bonds are nonpolar covalent. 31. What is the predicted? Oh, 31. Skip it. We're not doing structure. 32. Helium has the highest ionization energy of all elements. It's true, yeah. Why? Because helium's the smallest atom of all elements on the periodic table, therefore it's going to be the hardest to strip an electron off. Skip 33. 34. How many resonance structures does HCO3 minus ion have? Resonance structures is just which atom you make your double bond with. Sometimes you have a choice. Did I draw the resonance structure for HCO3 minus?
I don't think so.
Did we do that one? No? Let me draw it. Hydrogen is 1 electron. Carbon is 4. 3 oxygens, 3 times 6 is 18. Minus 1 charge is 1 electron. 22, 23, 24 electrons total. And, let's draw. What should we put in the middle of this? Carbon. Then I'm going to, let's throw a hydrogen on there, and an oxygen, and an oxygen, and an oxygen. Something like that. Does that look good? Does that look good? No, it doesn't. Why? Why does that not look good? I'm missing electrons. Okay, so let's go ahead and fill in the electrons.